So with that, it is my pleasure now to introduce the first presentation. My introductions will be very brief because you have the long introduction on the website. I would like to introduce you to my colleague and friend, Stefano Schiavon, Professor Stefano Schiavon. He is a professor both in architecture and civil and environmental engineering at UC Berkeley, and a big participant to our program in Singapore. And with that, I'm going to stop sharing and I will turn it over to Stefano.
Thank you, Kostas. So in this workshop, we're going to talk about the built environment. And the built environment is one of the most important national assets. It's very important for companies, and it's also important for people. Buying a house is one of the largest investments that people can do. The built environment involves also a large part of the working population. Globally, roughly 7% of the working age population is involved in the design, construction, management, maintenance of buildings. And we have been designing, constructing buildings for thousands of years. The oldest book about how we design these buildings is more than 2,000 years old. The fact that so many people are involved, the fact that it's such important from an economical point of view, and the fact that it has been done for so long would guide us to think that we are doing buildings that are efficient, that are cost effective, and very comfortable. In this presentation, I will give you evidence that that's not happening, that there is a high level of dissatisfaction yet, and I will give you some idea on how we can improve those buildings. And in the second part of the talk, I will spend some time on giving some ideas and potential barriers for the digital transformation of the built environment. As Kostas mentioned, we spend more than 90% of our life inside buildings. And these buildings affect our health, affect our well-being, affect our ability to learn, affect our ability to get our job done. And the Center for the Built Environment here at UC Berkeley has been going around for more than 20 years asking people if they like or not the space that they occupy. One of the first things that we should do is asking people, do you like or not the space that you occupy? And here we report the result, a summary of one of the largest databases in the world about this, and a database that is mainly focusing in the United States and in commercial building. And what we found is that only 2/3 of the population are satisfied with their built environment, meaning more than 1/3 is dissatisfied with it. And when we look at the specific area of the built environment, like for example, dissatisfaction with temperature, or dissatisfaction with privacy, or dissatisfaction with air quality, we found a large number of people that are unhappy. So there are many opportunities to improve the built environment. We did something similar in Singapore, and also in this case, we mainly focus on a high-end office environment, and the results are slightly better, but the main idea is the same. Here we have 3/4 of the people that are still unhappy with their space, and we have large dissatisfaction with the temperature and with privacy. This is not a new result. We've been seeing this trend for almost 20 years now. And roughly 10 years ago, with the emergence of certification program, like for example, the LEED certification program, we expected to see an improvement because we had the hope that by verifying if a building meet or not the criteria for which it was designed, we would find a higher satisfaction level. Unfortunately, we found that also in LEED certified building, even in highly certified building, the one that got the highest certification program, we did not see a substantial difference between the one that did not have the certification. So what can we do? We are in a situation where buildings use a lot of resources, are among the most important assets that people, corporation, and nation has. Many people work on them. They use a large amount of energy, and still we have many people that are unhappy about those environments. There are many potential solutions, and today I'm going to present one that we've been focusing here at the Center for the Built Environment and in Singapore in the last 10 years. The idea is that we should not create the same environment to everybody. Right now, we get the same temperature, we tend to get the same relative humidity, often we get the same lighting and air quality condition throughout the space. But we are different. We have different needs, we have different expectations, and we should personalize the environment. We developed the concept of personal comfort system. These are a device that instead of focusing on conditioning the entire space, they focus on conditioning people. Here, what you see over here, a couple of prototypes. We have a foot warmer, we have a desk fan that has an occupancy sensor, and so people, if they feel hot, they can turn it on and off. Or there on the right, we have a chair that can heat and cool people. One important characteristic of this personal comfort system is that they use very little amount of power and they only regulate the environment a couple of degrees. This system does not substitute in most of the situation the centralized system. They just give a higher level of granularity control that is directly in the hands of people. Some of these products try also to go to the market. We tested this product both in the lab and in real buildings. What I'm showing here is an example that we did in Singapore almost 5 years ago, where we brought a high number of students into a room where we gave them a fan. And we started our experiment in a typical indoor condition in Singapore that is around 23 degrees, and we found that only 85% of the people were satisfied. When we increased the temperature and gave them a fan, the satisfaction went to almost 100. When we removed the fan, then with the same temperature, then the satisfaction was reduced to 93. And then we got to an even higher temperature set point. And also in that case, the fan was providing more comfort than the case without the fan. Why did we increase the temperature set point? We increase it because that is among the most cost-effective way to reduce energy consumption in buildings. We've been studying how to make better building for a long time, and increasing the temperature set point in summer and decreasing in winter is among the easiest and most cost-effective solution that we can imagine. But if we do that, people will be uncomfortable. And so fan in summer can be used to cool people down. And so in this experiment, we learned that people are happier when they have access to fan, and they also use less energy. We test this also in a high-end research office environment in Singapore. This one is the R&D office for a large corporation in Singapore. And in that case, they already have the fan installed. In this case, they were not personal, but they had a granular control. Basically, one fan was conditioning up to 1 to 4 people. And also in this situation, we notice a significant increase on satisfaction. In the baseline condition, only 58% of the people were happy. When we gave them the fan, we increased the satisfaction up to 90%. So also in this case, we increase comfort and we reduce energy consumption. So this is the issue of personal comfort systems, devices that can condition people locally. Another problem that we are facing is that the model that we are using to control buildings can be outdated, are outdated. For example, here we show some evidence about the most common thermal comfort model that is used out there. It was developed more or less 50 years ago. And the idea behind it was that people were tested in a laboratory condition, a model was built and then implemented in the real world. There was not an approach where the information or the model that was developed at that time has been adapted to specific conditions. Moreover, this model accepts as an input 6 parameters. Among them, some are very easy to measure, like temperature, but others, like clothing and metabolic activity, are very difficult to measure in a real environment. So most of the time, they are just assumed. And we end up controlling building just based on temperature and relative humidity. We wanted to change both of these situations. And we introduced the concept of personal comfort model. These ones are models that can accept different type of input, basically whatever is available, then we use it to develop the model. And then the most important aspect is that they learn in time. So if new information, new evidence come in, or we have access to this information, then we can update them and tailor to the specific need of a person or a group. This type of model can be applied to commercial building, to residential building, but it can be applied also to other building environments like cars and airplanes. So a personal comfort model is a new approach to thermal comfort modeling that predicts individual thermal response instead of the one of an average population. One of the largest flexibility of this approach is that it can accept different type of input. It can accept physical parameter, environmental factor like temperature, like relative humidity, like outside temperature, like the amount of rain, like the amount of solar radiation. But it can also accept the occupant behavior pattern. For example, how people use the Nest thermostat, or the feedback that people give on an app to say if they are comfortable or not. This type of approach can also accept physiological parameters like heart rate or skin temperature. And we've been doing research on all of these different types of input. And now I will go over some of those studies. 5 years ago, we attached a sensor to a group of people in Singapore, and we followed them for a couple of weeks. We measured CO2, temperature, and relative humidity, and we asked them what they thought about the environment. When we tried to relate the physical parameter to their feedback, it was difficult to find a pattern. But when we tried to develop a model for each person, then we became much better at predicting what they wanted. In another situation, we have this heated and cooled chair, and we equip roughly 40 people in a commercial building here in California. And for a couple of months, we observed them how they use the heating and the cooling. In this case, the input to our model was the ability of people to turn on the local heating and the local cooling. And with those information, we were able to predict very accurately what people wanted. We also tried to go even closer to people. And we have done studies where we have a wearable device like heart rate, like skin temperature, like near body temperature. And with those, we get close to people and we were able to predict their thermal sensation quite accurately. This type of model have proven to have a higher prediction accuracy than the more traditional model. They also have proven to be very flexible and to adapt to the type of input that are available in a building. But unfortunately, they tend to require a lot of data. And so recently, in collaboration with a colleague in Singapore, we were able to develop a concept of cohort comfort modeling, where we develop, based on previous knowledge, some model, and then based on specific characteristic of a group, we can apply this model to them. For example, if you are a person that tend to prefer cooler environment or tend to prefer warmer environment, then we adapt a model that was developed for that cohort. And then if data are available, we also allow them to get update. Until now, I focus on predicting comfort, providing a higher environmental quality. But does this system save energy? The answer is that not necessarily. In some conditions, yes, they save energy, and we are focusing on solutions that save energy, but not always this can be achieved. But if the right personal comfort system is selected, then we can save energy. Here in this graph, I'm showing the idea that I described before. The fact that if I increase temperature set point and I provide an energy efficient solution for people, then we can obtain substantial saving. We are testing this idea in Singapore, and recently a study was concluded by a colleague here at the Center for the Built Environment in the Central Valley in California, where for more than 2 years, we observed the 13 air-conditioned zone, where at the beginning, they just had air conditioning, and they kept the temperature at the typical 23 degrees C. And then we gave them fans. And what we noticed is that, first of all, people tend to increase the temperature set point in the environment, and we obtain a substantial energy saving. These are our measured data, and an energy saving around 40–50%, depending on the condition. And the comfort was the same in both situations. So we can or increase comfort or reduce energy consumption and keep comfort the same. One limitation of this approach is that many of these devices require people giving feedback. And here we have an example of a company that was a spin-off from Berkeley and now has been bought by Siemens. In this case, people say if they want warmer or cooler, but that tend to distract people. And so we've been studying solution where instead of asking everyone to give a feedback, we have a kind of a monitor at the entrance of a space where people can say if they are happy or not about the environment. This is something similar to what you find in airports or in restrooms around the world. Another problem is related to the fact that if we ask too many times to people, people will stop answering. And we've developed a solution where we ask questions only when we need that information, when we have not enough understanding of how people will behave at specific, for example, temperature range, then we will ask a question. And we applied this to our previous study. On the right over here, we have the one that we had the wiring, the wearable sensor used by people. And then the second one is the one where we had the heated and cooled chair. The third one was when we had the skin temperature measurement. And we measure how effectively we as people with this index I, and the higher the value, the better. And when we implemented our algorithm, we were able to achieve the highest effectiveness on asking people. So until now, I give you some evidence that people are not very happy in the built environment, and a solution that could be applied that at the same time increase occupant satisfaction and also reduce energy consumption. In the next part of my presentation, I will spend some time on describing some of the barriers that may exist in buildings. One approach that we applied or we used for improving the smartness of a building is to apply machine learning to existing sensor. Basically, we have a stream of data coming out, for example, from an energy meter or from a lighting meter, and then we try to extract information from them automatically. And usually, the more sensor we have, the better. But I think that there is a limitation to this approach. For example, look at this space. We have many people, and over here on the top left, you see probably 1 or 2 air conditioners. If we add a temperature sensor to every desk, we may improve our ability to control the HVAC system. But given that this system can only have a kind of on-off control and does not have the granularity to create a personalized environment or a group environment, usually the benefit of increasing the number of sensing is not so high. And so if we want more sensing, we need at the same time to have a more granular actuation. We need systems that can turn on and off, they can regulate their output, and they can regulate that at personal or group level. Another limitation that I noticed in these years of interaction with the community that tried to do the digital transformation is related to the type of variable that we try to optimize. Often, the most common one is energy. Why? Because energy is simple to measure. We can measure it in an accurate way, and it's an important goal, try to reduce energy consumption. But from the perspective of a CFO or CEO, salary and benefit for people are the largest source of requirement for a company. Usually, the ratio between the amount of resource and money that go for energy compared to the amount of money that go for paying people salary is 1/100. or in some condition 1/500. So if in our pursuit to improve the environment and reducing energy consumption, we make people less productive, then we will create an overall damage to the company. And so even if measuring productivity is hard, that's an important goal that we should try to achieve. Often, when we apply machine learning to the built environment, we focus it on streams of data coming from sensors. Here you see an example of a device that we built roughly 10 years ago, where we measure airspeed, we measure mean radiant temperature, we measure CO2 in luminous and dry bulb temperature. The problem of this approach is that many of these sensors are only weakly correlated to how people feel. And we make building for people, and how they feel is what matters the most. In particular, there are some characteristics that are so weakly correlated that one could wonder, do we need to measure them? For example, I can put someone in a room at 70 decibel playing Bach, and then I can put the same person in a room with a white noise or a leaf blower at 70 decibel. The measured parameter is the same, but the experience that people will have will be very different. And the same can be seen for many of the environmental parameters, in particular the temperature, the lighting, and the acoustics. And so it's important that sometimes we use as an input the physical parameter, but other times we need to solicit the feedback from people, like, for example, in this example developed by one of the next speaker, Clayton Miller. A very important barrier in the digital transformation of the built environment is our ability to scale up solution. And to understand how bad is the situation in building, I will make a parallelism with Tesla. Suppose that Tesla developed a new algorithm to better control an autonomous vehicle. And if Teslas were building, then each of those Teslas should be brought back to the manufacturing facility, and you would have one engineer that go over the Tesla that is a unique prototype, where each sensor in the Tesla will have a different name from all the other cars out there, and how the sensor will be connected, and the type of engine and batteries and brakes will be different in every case. And that is how we are doing building. Each building is unique, and there is not a standardized way to name things and to describe their relationship. So even if we do not add new sensor in buildings, we already have a lot of information about this building. And if we can tap in an effective way over this information, then we can operate that building in a more energy efficient way. We can detect when buildings are going wrong. But right now, this is not possible, because even if we have a solution, every time that we go to a new building, we need to invest a significant amount of time to try to understand what is there, how it's connected, how it's named, and how it's working. And there's been several efforts to try to overcome this limit. One of them came out from Berkeley, is the brick schema that basically describe different points in the environment where these elements are located and how the equipment relate to those elements. If this type of standardization is applied widely, then we have the hope to be able to implement at scale some solution. For example, for many decades, we have been looking at comfort and sensors that come out from buildings by classifying if the temperature is within a specific range, for example, 70 to 75 Fahrenheit or 20 to 25 degrees C. And if the measurement is outside that range, then we say that the space is uncomfortable. Recently, we tested this assumption by at the same time measuring for many years the environment inside buildings and then looking how these relate to thermal comfort. We found that a more useful metric was the variation of temperature during the day, instead of is the building within a specific range. Why? Because if we know that the building tend to run hot in summer and cold in winter, we have way to adapt. For example, we may dress more in winter, or we may stick a heater under the desk, or in summer, we may buy a fan and put on the top of our desk. On the opposite, if there is too much variation within a day, then it's much harder to adapt. Unfortunately, this idea cannot be applied to all the existing buildings right away, because we will need to go one by one and implement it. Another problem in building is that there is not enough design automation. Our industry is extremely fragmented, is mainly composed by small players that have loose relationship among them. And that's resulted that buildings are not designed in an efficient way. We design building almost in the same way that we were designing integrated circuit in the 1960s. We are not very efficient, and we could apply some of the ideas that were developed for the electronic design automation. Idea like the platform-based design developed by one of the next speakers, Alberto San Giovanni Vincentelli, can be applied to building. And we could, using standardized element and standardized way, to put them together in order to create unique products. The last barrier is the one that worries me the most. And it's related to building codes. Buildings are designed based on specific building codes, and these building codes has been developed before we became a global community. Building codes are different almost at every state and often different at every county. We have a permit that happen at the city level. So a building that can be built in Berkeley may not necessarily be allowed in San Francisco, and most probably will not be allowed in Reno, Nevada, and almost for sure cannot be built in Paris, in France. And that is kind of unacceptable. We do not expect that we design car differently for every single city, or that every city has the right to approve or not a specific solution. We need to create more homogeneity in the standard that we have, and we need to have the permit process move from the city to at least the state level, and even better at the federal level. And given that the approval is subjective to the people that review the process, this process is inconsistent. And so the same building may be approved once in Berkeley, but if you have a different committee, it may not be approved another time. And so developing code that can be automatically assessed if you comply or not, and making that more homogeneous throughout the country will allow a higher penetration of the digital transformation revolution. In this presentation, I showed that there is a lot to be gained in the built environment. We are not very efficient in the way that we design and build buildings. Buildings are not of very high quality. They tend to use a lot of resources. More than 75% of the electrical energy use is used in building. More than 40% of the greenhouse gas emissions are related to building. And people tend to not be very happy about the building that we design. Only 2/3 of the people express satisfaction with the product. And we hope that the digital transformation can provide us much needed improvement in all of these aspects. We need buildings that are more efficient, more cost effective, and that can protect the health of people. Thank you very much.
Thank you, Stefano. Really appreciate the presentation. I would like to kick it off with one question and then turn it over to the audience. You mentioned the difficulties in homogenizing codes and having a more systematic approach of designing buildings. And you mentioned the analogy between buildings, or the lack of analogy between buildings and, let's say, electronic design automation. In electronic design automation, a major concept was managing levels of abstraction.
Yeah.
Meaning that we design something at a very high level of abstraction, but the ultimate implementation might be different depending on various other parameters. Does this exist today in the building community, these levels of abstraction?
It's not very common, but we would benefit from it. For example, we could think a building from the structure point of view. And we have practice, so kind of a standardized way that we think, this is a steel construction, this is a concrete construction, this is a wood construction, and so on. But then there is not a kind of a systematic integration between different levels, and there is not often communication among these levels. For example, suppose that you're designing the lighting system and you need to know, are people there and how many people are there? And therefore you need an occupancy sensor. And then you have another system, for example, the ventilation system, that we can decide how much air enters the space based on the number of people. These two devices, these two approaches will not share the information often. And so you will end up with one that has the sensor for the ventilation and one that has the sensor for the lighting. And this level of abstraction does not often communicate to each other.
Thank you, Stefano. So I would like to turn it over to the audience, and I believe the audience can ask questions via the chat, or you can ask to be unmuted, but please go ahead.
Hi, Stefano. Thank you so much. I'm Helia, and thank you so much for a great presentation. I was following your work and CB work for a long time, and I just enjoy it so much. I wanted to ask, in terms of like using fans, even operable windows or any kind of personal devices, I wanted to ask, like, what are you thinking about like holistic view of using them? Because as I know, some people said, okay, we don't use fans because it just blow the papers on the desk, or it just throws some dust in terms of ceiling fans. Actually, my research is on that. That's why I was thinking about that while you were talking about, because I was talking with teachers at schools and they were like, yeah, we would love to use fans, ceiling fans, but there are some allergies. There are some people with allergies in the classroom, and because of all dust and all those sort of things, or even opening the windows. And I mean, in terms of the holistic view of the thermal comfort and indoor air quality, of course, but there are other layers such as health and safety, security, and those sort of things. So I would like to.
Helia, thank you. We think that this type of personal comfort system does not need to apply in every single condition and every single environment. Specifically in the case of, for example, ceiling fan in classroom, we have seen situations where they can be applied safely without moving the paper. We learned that fans work the best when they move little air, not a lot of air. So we do not expect a very high airspeed in the environment.
Yes, hello. Hi. Igor Sartori from Oslo. Thanks, Stefano, for a very interesting presentation. I would like if you could, to elaborate a bit more on the point where you said that unfortunately, a scheme, a framework that you presented may not be applied on existing buildings. Maybe I just didn't get exactly what you meant, but what is the additional difficulty on buildings which exist compared to those built new?
And you're referring to the personal comfort models, to the device, or to the ability to scale up the solution?
I think it was about the ability to scale up.
So the problem is that suppose that we develop a new control algorithm, I don't know, let's think something fancy, something that we can better control the temperature and at the same time save some energy. And this control algorithm is based on temperature sensor and VFV box position. The problem of going from one building to another is that when we apply to one building and we learn how to apply it, then we go to another building, and that building will have a different way to name the sensors that there are in the building. This sensor will not be always describe how they relate to the equipment that we are trying to control, and we may not have information about the equipment, the characteristics, how big is the VFV box, how much can it regulate. And so the lack of a kind of a common language to name things and to describe their relationship basically require that every time that we try to implement in a new building, someone else needs to sit down, usually needs to be a trained engineer, and start to describe and understand this relationship. And the problem tends to be even bigger in existing buildings because we do not have a standardized way to describe them. Often we have information on paper, and sometimes the person that decides how to name things or the things that are installed has not been documented properly. So it's very challenging from this point of view.
Thank you, Stefano. There are two questions on the chat, if you can see them, if you can briefly address them.
Yeah, one of the questions from Gabriel is, what have been the challenges of commercial adoption of personal temperature control? And here, Gabriel, are you asking about the device or the models, the personal comfort models? Let's try to address both. From the point of view of the device, the highest problem is that they tend to be managed alone. So basically everyone has, or many office people have some kind of device. Often they are not very efficient. So for example, we went around campus and we look at what's happening under the desk of people. And something around 40% of the people had a heater. The problem is that that heater is very inefficient. It uses a lot of power. And if the heater is on and off, the system, the HVAC system, does not know that information. And so we think that personal comfort systems are already out there, but not always they are energy efficient. And so we focus on designing energy efficient solution. And we want them to be connected to the HVAC system, because in that way, the two can talk and create a more optimized solution.
There is a question about from Professor Panda.
So the question is, the abstraction is not there now, but can be incorporated. The occupancy detection can be used for both lighting as well as AC and V. I think so. I think that is not there yet, but if the system can talk to each other, we can have some efficiency. And we have tried that at the BCA building. And for example, think about the solution of having a camera. Right now, cameras are mainly there for security, but we could use in a private, safe way, camera to count people, to maybe recognize people. So if you have a specific need or desire, that needs can be met. And we can, for example, also use camera to check if people are not too close to each other in case we are in a pandemic situation, or if someone left something on the desk and move and go to another room, the camera can automatically detect that and give back and inform the person that they forgot things. So we have the opportunity to create efficiency in the built environment and have a deeper integration among the different sensors that are present in the building.
So thank you, Stefano. I see one more hand, but we are out of time. We have to move to the next presentation. Perhaps, Sunshine, if you can ask your question via the chat, maybe Stefano can address it via the chat.
Yeah.
And so thank you for that. And Stefano, thank you for the excellent presentation. I think the message that I got is that the built environment is complex. And it is not, it's even more complex, perhaps like a manufacturing facility. We will have rules and regulations that are uniform and clear objectives.